My name's Jason. I've been working on Search since 2013, and I've been contributing to Solr specifically since 2014, which is maybe less than some of the committers I see in the room here. But I've spent a lot of time with SolrJ specifically, so I'm hoping that I can teach something to everybody in the room today. So that's me, and I'm going to assume since you're here that you have some interest in SolrJ already, but maybe that's not a safe assumption. Maybe this isn't the best lineup of speakers right now, or maybe we're close to the launch table and people are trying to get a jump on the line. Who knows why people are here. So I wanted to try to start there and try to sell you guys on why you should be interested and why you should care about SolrJ and why it matters. There's a few groups of people and there's a few reasons, why people should care about SolrJ. The first and maybe the most obvious group of people that should care is the Solr community themselves. But not just for the obvious reasons that they're the ones that create it, they put it out there. I think often in the community, or especially in the community, SolrJ is maybe a bit of an afterthought compared to the other things that some people work on. But I think it has a much bigger effect than a lot of people realize. For most developers working on Solr, or rather using Solr, SolrJ is going to be kind of their main point of interaction with Solr. So if it's a pain in the ass to use, if it causes them a lot of trouble, that's going to be their impression of Solr generally. And when it comes time for their companies to decide whether they want to continue to use Solr or switch to something else, this is going to play a role in that decision. I'm not sure how big, but it's going to play a part. So that's going to affect the adoption of Solr, and that in turn is going to trickle down to the community. So the Solr community should have a strong reason to care about improving SolrJ and really making it a better product. The next group of people that should care are the same SolrJ users we kind of alluded to on the last slide. And really just for the reason that, like any library you pull into your code base, your day-to-day experience of working on that code and working with that product is really driven by the libraries that you use. If SolrJ is slow, if it's flaky, if it has a lot of race conditions, those are going to affect your tests that you're going to be working on day in and day out, and it's going to affect your product. It might wake you up at 3 a.m. in the morning if you're on call. So SolrJ's users have a real incentive to push Solr committers to really give SolrJ their best attention. The last group, and maybe the group with the largest reason to care, is anyone interested in the performance of their application. This could be the same developers that we looked on in the last slide, but it's probably a wider group too. It's going to include any kind of tech leads or architects or anyone else involved in your product. And they should care about SolrJ for the simple reason that client code is going to affect your performance as much as any of the other common performance culprits that we hear about in Solr, probably a little bit more. And you can see this on the mailing list. When consumers bring up performance problems on the mailing list, a lot of the people helping them will jump to maybe the common issues. They'll talk about their collection settings, and they'll ask about how often you're committing, and they'll look at your hardware sizing. But if none of those kind of bear fruit, then people will eventually ask, how are you doing your indexing? What does your client code look like? There's a lot of times where that's going to affect your performance as much as anything else. So for anyone who wants their application to really be as fast as can be, SolrJ is often a building block. It's not going to get you all the way there, but it's a good first step, and you need it to have a performant application. So hopefully those reasons, and hopefully those groups apply to everyone in the room to some extent. So now let's talk about what we're going to cover today. I wanted to do just a quick overview of what SolrJ looks like and where it came from and what it looks like. Then I wanted to dig into some of maybe the weightier classes in the library. And I really see these as being the Solar Client implementations. There's 4 of these that get used commonly, and they each have their pros and cons in different situations. So I want to introduce each one of these and discuss where you should use them and where you shouldn't. And really when to put them into your application. It's not just enough, though, to know how to use your Solr clients effectively. SolrJ has a lot of traps, problems, and really gotchas that catch even experienced users. So to save you guys some of this aggravation yourselves, I figured we could walk through a few of these just to make sure that you don't fall for them the same way others do. Lastly, we talk a lot about SolrJ is kind of a static library that people use, but it's still evolving and it's still changing based on the feedback we get from our users and based on what the Solr community needs from it. So I wanted to finish by looking at some of the ways that the client could be changing in the future. both in ways that are, near certain, that are, pretty much staged and ready for the next Solr release, as well as some things that I think are promising or that are really interesting, even if they haven't been championed by a committer yet or merged onto the main branch. Then, if we finish on time, we should hopefully get to some questions and comments. So looking at the history of SolrJ, the first thing that's striking is how old Solr is, or SolrJ rather. It's nearly as old as Solr itself, and that's, Solr was started in 2004, it was open source to the ASF in 2006, and SolrJ came along in 2007. And what really kind of underscores this age is the JIRA numbers that were used to initially commit the library. It was formed in Solr 20 and Solr 30. And that the interesting thing about these JIRAs and the reason that they're worthwhile to look at is because the library still looks incredibly similar to how it did back then. These two JIRAs really set the interfaces and the object model that we still use today. This is a usage example that I took from Solr 20 itself. There's a comment on the thread there. And I wanted to show this first because if anyone's familiar with modern SolrJ, you're going to see that almost nothing has actually changed since 2007. There's a class here that goes under a different name and has a different constructor today. But otherwise, this code would compile just fine in Solr 7.5. And that's crazy for something that was written 11 years ago, especially with the pace of development that we see in Solr today. SolrJ has been an incredibly stable client, and that's been awesome for its users. This is what this snippet looks like today. And again, the only difference here, I have it highlighted in green on the slide, is that line in the middle. So before we go any further, I wanted to kind of get a read of the room, maybe. Can I get a show of hands for who's worked with SolrJ before? Is anybody unsure of what the snippet's doing, or should we walk through it real quick? Anybody want to walk through it? Okay, great. So I think the real interesting parts of the SolrJ library are really in the trade-offs between the different Solr client implementations. Those are where you, as a consumer of SolrJ, really have to make some decisions about what you want your application to look like. So I think the next thing we should take a look at is kind of the Solr client interface and its implementations in more detail. Solr client's actually an abstract class, and it and its implementations are responsible. They send all requests to Solr. Most of your Solr requests are going to be of only a few types, so most of the methods kind of in this abstract class are just kind of convenience methods that make some of these common tasks easier. You can index docs, you can search, you can delete docs, all that kind of stuff. And the interesting part here is that all of these are implemented in terms of there's only one abstract method on the whole class, and that's this lower level request method. And all of your requests to Solr are going to go through this one method. So when we look at the Solr client implementations and talk about how they're similar and how they're different, really their differences all come from how they implement this one specific method. And even looking at the implementations for this method, they share a lot of similarities. They use a lot of the same kind of helpers and patterns in making their requests to Solr. The variation often comes in how they build off of this basic pattern. So in looking at SolrJ, I wanted to kind of just show, we'll go through an example of how a single request is going to make it up to Solr through SolrJ. And then we'll look at how each Solr client implementation kind of varies that pattern and where they take it. So as an example, I wanted to do follow an update request through SolrJ. It's going to start out as this green box here, this update request object. Now the first step in sending this off to Solr is that all Solr client use the Apache HTTP components library, for sending their requests. So we have to build an HTTP post and we have to send it along through an HTTP client. So the first step is going to be building this HTTP post object. There's really two pieces of this that are somewhat interesting. The first is the URL string here that we have to build. This is going to be built from a couple different pieces of metadata that are pulled from various places. Each Solr client usually has a URL or multiple URLs associated with it. So that's where the base comes from. And then we get a path suffix and some query parameters from the update request object itself. So that's used to build out this URL. Next, we need to actually build the entity of our HTTP post, the real body of the request, and that's where most of the meat is here. Each Solr client has a request writer, and that chooses the format of a request, whether you want to send your request as JSON or XML or Java bin, which is the default for most Solr clients. So our request writer in this Solr client is going to create a content writer. And that content writer is just really going to be a wrapper around our update request. So we end up with kind of an onion object as our HTTP entity here. We have kind of the wrapping HTTP entity, and inside that is kind of this content writer interface. And inside it is the real nugget of content there, our actual update request. So that when this entity comes along and needs to be written out on the wire, our content that we need to write is kind of buried in there. The entity has a write to method in its interface. So when the HTTP client goes to send this, it's going to call that write to method, and it's going to immediately delegate to our content writer. And then the content writer is going to do two things. The first is it's going to convert our update request, the content, so all our documents, all the IDs we want to delete. It's going to convert those to a named list, which is kind of a generic structure that SolrJ uses to represent requests and responses. So once we have it in a named list, we're going to delegate the work to a class called our Java bin codec. And this codec was chosen by our request writer, and it knows how to serialize named lists into an output stream. So we do things in this way really because it's kind of complicated, but it makes the request sending much more memory efficient. You'll notice here that at no point are we kind of taking all our documents, forming them into a big string, and storing it in a buffer in RAM anywhere. The Java bin codec goes through our update request, or our named list rather, piece by piece, so that it never has to assemble the whole request body in memory. And this matters a lot if you're sending batch updates to Solr or making other kind of larger requests. We'll see the process play out pretty similarly in reverse when we read in, or we parse the response that Solr sends back to us. Clients have much like the request writer we just looked at, they have a response parser. And just like the request writer, this chooses the codec to read in our data with. So the response parser chooses this codec, and that's going to look at the stream that we're given by our HTTP client. So our Java bin codec is going to go through the response, and it's going to read a series of, there's going to be tag bytes, which kind of indicate the data type that we're going to read next, and then the size of that, and then the actual chunk of data. And as it goes through these pairs of tags and data, it's going to reassemble that into a named list. So you notice again here that at no point are we reading the whole response into memory into a string or a buffer anywhere. So this has the same memory efficiency that we saw when we were writing out requests. So this is the pattern that all of our Solr clients really follow in sending individual requests and in receiving the responses. And it's the things that these clients do on top of this basic pattern and how they deviate from it that really differentiates them from one another and where their various pros and cons come from. There's 4 kind of main Solr client implementations that you're going to use in your code. So let's take a look at each one and see how this modifies that basic pattern in the results of that modification. The first Solr client to really look at is the HTTP Solar Client. And this is really kind of a baseline implementation. There's not much specialized functionality. There's not much, there's not much addition to that basic pattern that we just looked at. A lot of the other Solr clients are really built more around specific use cases and really kind of niche situations. In the HTTP Solar Client, it's really best left as a fallback for when none of those other implementations that we're going to talk about soon, it's really left as a fallback for when none of those other implementations are appropriate. And that's not a knock on it to say that it's a fallback. There's still a lot of situations where it's probably the best option for you to use. For example, if you're maybe in an embedded scenario and you only have one Solr instance, HTTP Solar Client is perfectly acceptable for that use case. Another time you'll see it sometimes is if people have a larger Solr standalone, maybe master-slave setup, but it's behind an external load balancer that only has a single URL. That's another time that you'll see HTTP Solar Client used well. The biggest advantage of the HTTP Solar Client is really its flexibility. It's not making any decisions for you about how to handle particular error cases. Its simplicity is really its main advantage. The biggest disadvantage, though, and kind of an obvious one, I guess, is that you can only point it at a single URL. It's not meant to talk to multiple Solr instances. And that makes it susceptible to any kind of network issues or any kind of Solr crashes that you might run into. So if you have multiple Solr instances, but the one that your HTTP Solar Client is using goes down, then your whole application is going to be down until that single instance comes back up, even though you have other Solr clients that are, other Solr servers that are ready to serve requests and could answer queries from your users. The response to this that the Solr community took was the load balancing Ttp Solar Client. And this really comes up with an answer by really it's just a wrapper around a group of HTTP Solr clients. The load balancing client, it has a list of these Solr clients internally from URLs you give it at startup. And it uses these to send requests, and it's going to use each one kind of in a round-robin fashion. So if you send multiple requests, they'll each use a different Solr client to send their request to a different Solr server. Now, when errors occur, a normal error, like a 400 or a 404, or something that's, I guess, expected in some sense, they're just going to get returned to the caller as is. The Solr client will throw an exception. But if one of your requests fails with an error that maybe indicates that your Solr instance is down, for example, a connection exception, if you can't connect to your Solr instance when you go to send your request, then the load balancing client is going to assume that that's what happened, that your Solr instance went down. And it's going to look at these other clients it has internally and say, oh, I can fail over to these and retry that request. So it's going to resend this request on the other clients you have, and it's going to do so until either one of those clients succeeds, or they all fail, or if you specified a timeout, until that expires. And as it goes through it, it also remembers which Solr instances were dead or were unhealthy, and it'll keep those in a separate list. And it will avoid using those for any subsequent requests until they're healthy again. It has a health check that it runs in the background to check up on this. This improves on what we saw with the HTTP Solar Client by eliminating the single point of failure we saw there. You can have multiple Solr instances down, as we do on this slide, and still get responses back to a user query. It also gets you some primitive load balancing, and that's where the name came from, and that's one of the primary drivers when this was initially written. The load balancing client, it's useful when you're querying a standalone cluster with multiple Solr instances, with a larger master-slave setup, for example. But really, its usefulness doesn't apply much beyond that. And that's because of this simplistic round-robin approach that it takes. It assumes when it does this round-robin strategy that all of the URLs that you give it, all the Solr instances behind those, are effectively interchangeable, both in terms of specs and in terms of the data that actually lives there. If the specs on your Solr servers are different, then your load balancing is going to be out of proportion to that, since it's so simple, and you're going to get some wonky results. If the data on your Solr servers is different, then you're just going to get sporadic 404s, as the client isn't smart enough to know which collection lives where, which shard lives where. A lot of these assumptions about the interchangeability of your Solr URLs, they really make sense in Solr standalone or when you have only a couple servers, but they really rarely make sense in Solr Cloud, where your sharding and your replication make your data placement more complex. So we need a different kind of Solr client for Solr Cloud. So the Solr community built a third client that's really designed with Solr Cloud in mind, and this is the Cloud Solr Client. It's unique in that it's going to monitor the topology of your Solr clusters. It keeps track of which nodes are in your cluster, but also which data lives on each of those nodes. And it's going to use this cluster state information to route your requests more intelligently. As an example, when you go to send an index or a add document request to Solr, the Cloud Solr Client will look on the client side to figure out what shard that document needs to belong to. And it'll look up the nodes where that lives and which of those nodes is the shard leader. And it's going to send that data directly to the shard leader. This differs from non-Cloud Aware clients, where you would send the request to any arbitrary node, and then it would have to be routed to the leader to begin kind of execution in Solr Cloud. So using the Cloud Solr Client and using this intelligent routing is really going to save you network hops and allow you to finish your indexing quicker. The Cloud Solr Client should really be the client of choice for any kind of workload on a Solr Cloud cluster. The lone exception that we might see is heavy indexing, and we'll talk about that in just a minute. So again, we have this efficiency for our Solr Cloud use case, but the downside here is that the Cloud Solr Client, it's not just tuned for Solr Cloud, it's not just better for Solr Cloud, it's specific to it. You can't use it with any kind of Solr standalone setup. It just won't work. Another downside of the Cloud Solr Client is really its heaviness. It's constantly requesting this cluster state information from either Zookeeper or Solr or both. And this is really heavy caching. It makes it probably one of the heaviest objects to use in SolrJ, and you're going to want to create as few of them as you possibly can get away with. There's a few kind of settings on the Cloud Solar Client that are able to tune this, but these are really just kind of band-aids around the whole problem. No matter what configuration you set when you're creating your Cloud Solar Client, it's still going to be an incredibly heavy object to use. One issue with all the clients we've looked at, or one assumption of all the clients we've looked at so far, is their expectation of synchronous workloads. They're going to block the calling thread until Solr responds with data back to you. And this makes sense for most use cases. For example, if we're trying to display query results, we need Solr to come back so we can display them on screen. But there's a lot of use cases where this doesn't make sense as well. For example, if we're indexing, Solr doesn't really return much useful information in indexing or in an update response. So from a client perspective, it's just kind of useless to sit around and wait for that response to come back. So the Concurrent Update Solar Client takes advantage of this by sending its update requests asynchronously. The update client, it keeps a queue internally of all the documents that need to be sent off to Solr, all the updates that need to be sent off. And when SolrClient.add is called, then this client is going to add to that queue, and it's going to spin up a runnable in the background to kind of take care of things here. The Update Solar Client returns with a kind of a dummy response to the original caller before necessarily anything is even talked to Solr. Eventually, a runnable is going to come online, and it's going to remove the documents from the queue, and it's going to stream them off to Solr. If there's other documents in the queue, it's going to attempt to send those in the same batch as well. And this brings some really big performance improvements. We're avoiding the overhead of kind of establishing unnecessary connections, and we're batching our documents together under the hood. This all comes at a cost, though. As you can see, the Solr client call returns before we ever talk to Solr. So if anything goes wrong in that communication to Solr, if we get a connection exception or our documents are malformed in some way, they don't fit our schema, then there's no real way to get this information back to the original caller. You see the caller's not even on the slide here when we're talking to Solr. The Concurrent Update Solar Client, it has an on-failure method that you can extend and maybe put some custom behavior in there as a hook for when these things go wrong. But the signature of that method, the way it's built right now, it doesn't really give you many options as to how to handle these. It's hard to think of anything that you could do there other than just log the error out, which I think is the default implementation. It's worth mentioning here that all of this behavior is really limited to how the Update Solar Client handles updates. If you're sending a query or any other non-update request, you're going to get the normal behavior that you would expect from the Ttp Solar Client. In fact, we use an Ttp Solar Client under the hood here. So those are the main Solr clients that SolrJ offers. And with those under your belt, you should know just enough to be, to get pretty far and to be dangerous, so to speak. But really, that's just kind of that's not a figure of speech. It's more of a bad pun here, because SolrJ is great, but it has its fair share of pitfalls and problems that often catch, people who haven't used the library for long, or even those who have. And they're pretty dangerous. They have some significant effects. They run the gamut from really kind of sapping your product's performance quietly to effectively dropping requests entirely. So we'll take a look at a couple of these next and hopefully save you that trouble yourselves the next time you go to use SolrJ. So this is the first common mistake that I wanted to highlight. I guess we're going to try to do some audience participation here. Can anybody see what might go wrong with the snippet or what might work less than ideally? Any guesses? I don't think so. That's outside of the 4. Right, there you go. We're only indexing one document at a time here. And that's going to be a huge performance problem for us. There's a ton of overhead involved in sending individual update requests to Solr. You have to establish a connection, and then Jetty has to process things before Solr even gets kind of a handle on the request. And then you terminate the connection. And if you're doing this for every kind of 140-character tweet or every kind of numeric update that you want to make to your index, it's going to be way slower than it needs to be. And it's a really common mistake to make, particularly because the Solr client interface allows it. It has an add method for that single document update. But this is a real killer performance-wise. There's 2 alternatives that the community recommends as best practices to avoid this single doc indexing. The first approach involves indexing your document changes together in batches and sending them using any of the other SolrClient.add methods. There's a lot of methods that take a list of documents or an array of documents. The second approach involves changing the client that you use to using the Update Solar Client. And that's really built for this use case. That's going to bring the asynchronous interface and the automatic batching that we discussed just a couple slides back. This approach, it's often an easier code change too, because all you have to do is change the constructor that you're calling. But you have to be aware, again, of the downsides with the Update Solar Client and make sure that those are appropriate with your use case. I've shown a little experiment here to really bear out some of the community advice around batching. Each point in this graph represents the throughput from indexing about 1 million documents to Solr with a variety of different batch sizes. And I think from the slope on this line here, it's pretty easy to see the big difference that batching makes. With a batch size of 1, so basically no batching, we're going to see a throughput of 1,100 documents a second. But going up to a batch size as small as 10, you immediately jump up to 8,000 documents a second. The important thing here isn't the specific numbers. This was just run on my laptop. But it's easy to see the change that batching makes in your throughput. I think, too, that the axes on these graphs really kind of belie how stunning of a jump this is. If you look at the x-axis, it's moving by increments of 2, but the y-axis is moving by increments of 1,000. So the slope of the line doesn't look that impressive, but it really is kind of stunning. And I think this next graph shows this a little better. The scale on this is really more visible, and it's going to include the experiment sampled out to a batch size of 1,000, whereas our last slide just looked out from 0 to 10. It also shows the indexing performance of a few Solr clients relative to one another. In blue, we still have our HTTP Solar Client. In that orangish yellow color, we have our Cloud Solar Client. And then in red, we have our Update Solar Client. So there's a few things that I think we can take from this graph. The first is, again, I think it makes it much more clear how beneficial batching really is. As soon as you turn on batching, with almost any kind of batch size, you're going to see a vertical spike in throughput here. And that's going to be really important for your application. The second thing to look at is, even once you turn batching on, you still get some additional benefits from fine-tuning your batch size. If you look at the HTTP Solar Client in blue, we kind of jump up to around 18,000. But as we choose a more appropriate batch size, we eventually get that to plateau out around 22,000. The last thing that is good to take away from this graph is kind of I don't want to use the word hierarchy, but the relative kind of performance of our different Solr clients. Even with batching, there's going to be differences in how your different Solr clients perform. Maybe the worst is going to be the HTTP Solar Client. Then in the middle, we'll have our Cloud Solar Client, which uses some intelligent routing that we talked about before. And then we have the Concurrent Updates Solar Client, which is really kind of built for this use case. Cloud Solar Client.
What's a maximum batch size? I mean, it looks like it levels off, so at like 20,000 for HTTP Solar Client, so 20,000 would be a good batch size?
So the question is, what kind of batch size would I choose, or what's the maximum that I could go out to? And I think the things to take away from for these graphs are things of relative performance. I think a lot of it is going to depend on how big your documents are and a lot of other things about your use case. So I think the real thing is just to experiment with tuning your batch size. I think it's hard to make a generalization and say that there's an optimal batch size for everybody.
So why don't you use a size to measure, like how many megabytes, each time you send? Not by number, but by the size of all the documents.
That's another way to do it, but that's not a thing that's really built into the client interface as it is. That would be a good thing to see, though.
How do I get those measurements of how fast it's going?
So if you're looking at what code did I use to do this benchmarking, is that the question?
Yeah, so if I'm trying to fine-tune the batch size I use, how do I get some type of feedback of, hey, this is how fast the work's going?
I think that's a good question. I think it's a little, let's talk after. I don't know that I have the time to talk about it right now. So little digression on performance there. Let's get back to another SolrJ mistake that's pretty common for people to make. Can anyone see what might go wrong with this snippet here? It might be a little tough to read the way it's squeezed onto the slide, but we're gonna index a batch of documents. So we're batching, so that's good. And we're gonna commit if the batch succeeds, and we're gonna roll back if the batch failed.
Committing from the client.
Right, right. So the suggestion was that it's a kind of problematic to commit from your Solr client. And you can say similar things about commit and rollback as well. They both have some downsides when you are invoking them from the client side. Right, right, right. Sure, and sure, and you're jumping ahead of me a little bit here. There's two kind of problems with commits and rollbacks. There's a semantics problem, which is that it rarely means what people expect it to mean if they're coming from a database context. And there's a performance problem as well. The semantic problem specifically, if you look at client-triggered rollbacks, they're going to affect all changes made by all clients since the last commit on your Solr collection or your Solr core. And that's rarely what newcomers expect, particularly if they're coming from a database background. This is particularly dangerous if you're running a multi-threaded client program, or you have multiple clients making changes to the same core or the same collection. Rollbacks are really dangerous. There's a very high chance that you're going to roll back accidentally someone else's changes. There's an additional race condition if you use auto commit settings, which are this really heavily encouraged way to commit in your Solr cluster. It's hard to know from the client when the last commit was. So often your rollback just won't have any effect if a commit happened right prior. Looking at the performance problems here, client-triggered commits are easy to overdo, as well as rollbacks. But looking at commits specifically, they're very heavy operations. And if they're done too frequently or they're done too close together, they can have a huge impact on performance. If you're committing in a loop, or if you have multiple client threads that occasionally trigger commits in what seems like a reasonable way, you can still often quietly just crush your performance. Almost always, you're going to want to ensure that your commits come from only one place to ensure that this overcommitting doesn't happen. And server commits are really the recommended way to do this, and in the best way, I think. So I think this is going to be our last SolrJ mistake, and this one is maybe a bit trickier. The snip is trying to delete a document and then recreate it with other values. And kind of on a slide here as a simplified example, this may look a little contrived, but I think in the real world there's plenty of situations where code like this might come up. For example, if you imagine you're running an online store and you're processing inventory events that are coming into you, you might get one update that just tells you, hey, we just sold our last copy of Harry Potter, let's take it out of the database. And you might get another notification right after that says, hey, we just got a new truck into the warehouse, we have a lot more copies, let's update the database with those. So there's a lot of cases in the real world why you'd have code like this. The question is just whether it's going to do what you think it's going to do. Can anyone see what might go wrong here? Sorry if it's too small. There you go. So update requests, they record the ordering of the things you tell it about, but they only record the ordering within each type of operation. So it'll remember that you wanted to add documents 1, 2, and 3 in that order, and it'll remember that you wanted to delete IDs 1 and 3 in that order, but it doesn't know how those kind of interleave with each other or what exact ordering they should be done in. So if you're depending on that exact ordering, you're going to be disappointed. SolrJ just kind of chooses in order arbitrarily to send these up to Solr with. So it's going to send all the document adds or all the document updates. Then it's going to send all the deletion by IDs, and then it's going to send all the deletion by queries. If you look kind of back at our initial example here, we would have expected all 3 documents to make it into the index based on the ordering in our code. But when this request actually gets sent off, only document 2 is going to make it into the index. So we're going to be quietly dropping documents here, which is really dangerous. The workaround for this, it's not a good one, is just to avoid mixing operation types if you're using a single update request. We talked about batching. Batching is great, and it's still the way to go. There's still huge performance benefits there. But you have to be very careful if you're mixing deletes and adds or other operation types. So you want to keep those in separate requests, or at least be aware of the order of operations that'll end up happening if you use this. So it's clear from some of these examples that there's really kind of a lot of work that still needs to be done on SolrJ. The community has a lot of ideas on how things can improve in terms of performance and trappiness and API cleanliness. So I wanted to finish today by highlighting some of the work that's being done by the community members out there. I wanted to focus specifically on things that are going to be coming and you can look forward to in the 8.0 release or in the 7.6 release, as well as some things that I thought were interesting and promising that haven't been worked on or not ready yet, but might be cool at some point in the future. I think most of the work and most of the discussion done in SolrJ today is really around performance. And some of these have a lot of potential. The biggest change, the one thing I want to highlight specifically on this slide is Dot's work to Kalman Dot, who's a committer. Some of his work to update the Solr clients from using HTTP1 to HTTP2. This is going to bring a lot of performance improvements. I don't know if anybody here was at Steve's talk right before this, but he talked about the move to HTTP2 in our Solr clients. There's been some benchmarking done, and people have seen up to a 50% increase in indexing performance, which is really kind of staggering. There's the usual caution that you have to put around benchmarks about, it's hard to tell whether this matches what you're going to see in production. But even if we only get a fraction of that, it's going to be a real improvement for our users out there. Usability are another thing that can really improve in SolrJ. These tend to get a little less traction than some of the performance improvements, but I think there's a good reason behind this. The Solr community takes their backwards compatibility seriously, and any change that's likely to improve usability often breaks those user interfaces that our clients depend on. So these receive some heavy scrutiny. I mentioned earlier that the Solr client interface is really similar to how it looked in 2007, and this is a big reason for that, and it is a huge benefit to SolrJ. That said, there's still a few discussions going on around usability improvements. And maybe the one off the slide that I wanted to highlight is how some of our errors in the Solr clients are reported. Right now, if SolrJ fails a request, the user is going to get an exception back, but it's not really clear what they should do with that. They can look at the message string, or they can kind of dig around in the exception, try to find a root cause that's of a type that they recognize. But those are both kind of brittle, and they're both kind of haphazard, and they're both kind of rough guesses. One of the ideas that's been proposed is that we add an enum field to the exceptions that we throw that maybe give hints as to how clients should handle particular errors. And some examples of what these might be, this was a client error, don't ever retry, it's not going to work. Or maybe Solr is unhealthy right now, try again later. Or try this again, but after a short period of waiting. So there's some rough guesses that we can give users that might improve on how we're doing things today. I don't think this change is really likely to come soon, but there's been some interesting discussion around it, and it would be a real benefit to users of SolrJ if this came at some point in the future. All that said, the really most impactful usability changes in SolrJ, I think they're unlikely to come from changes to the interfaces themselves, but really to the things that we build around those. There's Java docs that can be improved. There's ref guide examples that we really need to add and really improve the documentation. Because the biggest problem with SolrJ today, I think, is the problems and the trappiness that are out there. So if we can better document those, we'll better support our users. As a demonstration on this, these are the classes we talked about today. These are the ones with class-level Java docs, with method-level Java docs. These are the ones that get mentioned at all in the ref guide. And these are the ones with examples in the ref guide. So I'm not saying that all of these should be as fully documented as possible, but I think it's clear there's room for improvement here. So that's where I wanted to end today. I wanted to thank everybody for coming. Again, my name's Jason. If anybody has any questions, I'm happy to talk afterwards.